Hello, welcome to this video. I haven't put a video out there for the playlist of quantum field theory for the gifted ammeter for a while, but this is restarting that playlist. This is going to be part 6. If I've done my numbers right, there's 5 videos before in the series, plus I think one on introducing what the words quantum field actually means, so we know what kind of physics we're describing and what the central object is. Now in this part of the video we'll be reviewing another chapter of quantum field theory for the gifted ammeter. I'll mention the author as well of the book down in the description below this video, and for this part we'll be looking at field operators. Now, field operators are a way of creating or destroying particles, which is very important in particle physics because particle interactions involve the creation or destruction of particles very frequently. For example, if we have beta minus decay, a type of radioactive decay, a nucleus, if it has too many neutrons, can exchange a neutron for a proton, and in the process release an electron and an anti-electron neutrino. So these kinds of operators are very important for describing particle processes, some of which are fairly common, like radioactive decay, other which happen at much higher energies in particle colliders like CERN. We will also be starting, therefore, with a classical analogy going back to the idea of how, the quantum harmonic oscillator can kind of create or destroy pseudo-particles, but we'll be generalising this to how you create or destroy actual particles you'll find in the standard module of physics. So that's where we're going in this video, and we'll finish by talking about the potential and really ridding us with the concept of there being neat field lines between particles, and start instead to think about the forces as arising from our two test particles exchanging force-carrying particles between them. Thus kind of second quantizing potential. So we'll also talk about second quantization, which will bring us to a discussion of how we represent opposite operators that represent classical observables in quantum field theory. So, to talk about field operators, we really begin with an analogy in quantum mechanics, standard quantum mechanics. Indeed, quantum field theory is an abstraction of quantum mechanics, in much the same way that quantum mechanics is an abstraction of classical mechanics. So let's consider, or really review, the quantum harmonic oscillator. So there's a previous video, I think the last video in this series, about the quantum harmonic oscillator, so I won't go into too much depth. But essentially, with the quantum harmonic oscillator, we take something like a pendulum, which is swinging at a small angle, and make the pendulum smaller and smaller until it obeys the rules of quantum mechanics. Really, it's not so much size, it's the energy. If the energy of a harmonic oscillator is really small, it behaves like a quantum harmonic oscillator. Examples are like bonds holding atoms together, so this has very important applications in chemistry, and explains also why certain gases will absorb infrared whilst others won't. So this is a very useful bit of quantum physics. But in the quantum harmonic oscillator, the energy levels are quantized. So an oscillator in the quantum regime can only have specific an energy out of a discrete set of energy, and each energy we call an energy level. And there are wave functions, so our Greek letter psi, which looks like a trident associated with an electron, or whatever is doing the harmonic oscillation in each energy level. So we can think of an operator which raises the energy of a particle undergoing harmonic oscillation. And we can think of that mathematically as just, well, altering the wave function. However, we can think of it also more physically as the particle getting energy from somewhere. And because in the quantum harmonic oscillator, the difference in consecutive energy levels is the same, it means that to get from one energy level to the one above, the thing undergoing oscillation would always have to absorb the same amount of energy. And so we can think of almost like the gaps between the energy levels, consecutive energy levels corresponding to the energy of a particle that our oscillator can absorb to get to a higher energy and emit to get to a lower energy. So in other words, raising to a higher energy level is associated almost with this particle appearing being absorbed, whilst going to a lower energy level is associated with the particle being emitted and just vanishing or decaying or something. And this then leads to the idea of a kind of ladder operator which kind of creates a particle, causing the energy of our oscillator to go up, and the operator which destroys a particle, causing the energy of our oscillator to go down. And these operators, because of the way energy levels are even spaced in the quantum harmonic oscillator, are called ladder operators. But we can generalise this idea and move away from the specifics of the quantum harmonic oscillator and say, well, we can think of a generic operator, taking inspiration from our ladder operators, and we'll call this operator a dagger. And this operator creates a particle with energy, whilst A, if you like, the Hermitian conjugate of a dagger, so it's related to a dagger in some mathematical way, A destroys a particle, which in the context of the quantum harmonic oscillator causes the object to go down in an energy level. Now, in quantum field theory, because in quantum field theory, energy is a property which is very good at describing a particle, generalises very easily to the relativistic realm, and also the fact that due to the conservation of energy, energy is very special, it's natural to think about the energy, or kind of equivalently, for at least particles with mass, the momentum of the particle. And actually even more so for particles without mass, that's a very clear relation between energy and momentum. And indeed, actually, if we take C to be 1, then the relationship between energy, momentum and mass is very straightforward. So, when we're talking about creating or destroying particles, we tend to start with a discussion of creating or destroying particles with particular momenta, or to use quantum jargon, in particular momentum eigenstates. That means the momentum of the particle is well defined, so the particle has a specific momentum. And so in quantum field theory, the creation and annihilation operators will have a subscript, usually a vector momentum, below the operator. It's also worth saying that usually operators have hats above them, and for future videos I will probably put a hat above a creation or annihilation operator. But for this video, that's going to be so many operators, it's actually going to make it more confusing putting hats above operators. But it's worth saying, when we have less operators to worry about, or are not so exclusively worried about operators, I will put hats above the symbol for the operator. So these are our creation and annihilation operators. Now it's worth saying, if you come from a Christian background, you might see a dagger, that is A with the like cross above it and go, that feels like it should be an annihilation operator. I found that. I know a few of my other friends have found that, and that's probably because when we look at the dagger, it looks like a cross, and so we end up thinking about, the crucifixion of Jesus, which is inevitably associated with destruction, not creation. However, the way I tend to think about it, if you fall into that trap, is that the dagger is like an empty cross, so it's about the resurrection of Jesus, hence it's about creation. So a dagger is the creation operator, not the annihilation operator. So, it's just worth saying, um, it's also a good way, even if you don't come from, a Christian background, to remember what is creation and what is annihilation. Because often in a particle process, if you have a creation operator, you also have an annihilation operator, and it's important to remember which is what, and having the symbol A for both of them can be a bit confusing. So we talked about creation and annihilation operators, and I'm just putting a summary here of what these operators do. However, we've also said that in terms of experiments, well, we might not have said it, but it might be probably fairly obvious that kind of we as humans don't easily register where things are in terms of their momentum. We don't live in a momentum space. We live in physical space. So, although theoretically it's easier to start with creation and annihilation operators, which explicitly refer to momentum eigenstates, it's much more practically useful to develop something from them which will create or destroy particles at particular locations in space, so in other words, in position eigenstates. And the things that do this are called field operators. Now you might wonder, what does a field operator have to do mathematically with an annihilation and creation operator? Well, if you've seen Heisenberg's acidity principle before, um, then you'll probably know that there's a very intimate link between position and momentum. And so it turns out that the two quantities are in fact so interlinked that that if one defines creation and annihilation operators as we have done, one can use them to immediately construct field operators. Now, field operators have the Greek symbol psi, which is a trident-like symbol, which you might think from quantum mechanics is the wave function. It's important here, psi is not the wave function, it is a field operator. However, it's worth saying a field operator will create a particle in a position, well, eigenstate at a particular location in space. And we can always think of a wave function associated with that. So, a field operator creates a particle which will have an associated wave function. So, the symbol for the field operator, there's a reason why it's the same as the symbol for the wave function, but they are mathematically distinct. So for this video at least, and I'll be clear as the series goes on, but where you see psi, you should think field operator, not wave function. So if we want to get to field operators, we should first ask, well, how do position and momentum eigenstates relate to each other? Well, really we use the idea that if a particle is essentially in a position eigenstate, then it will be distributed throughout the whole momentum space. And if something is in a momentum eigenstate, it will be distributed across the whole position space. And it will be distributed in such a way that it has a plane wave in physical space or in position space. And the plane wave is the e to the ip dot x. It describes the plane wave associated with a particle with well-defined momentum or energy. And this goes back to the idea of when particles diffract or are moving freely with well-defined energy, they interfere and diffract as if they are plane waves. And the rules of quantum mechanics, really going back to the early days of things like the de Broglie kind of equation for the wavelength of a particle and stuff like that, tells us that through the wavelength of the wave, that the plane wave should be of the form e to the ip dot x, where p is the momentum of a particle. But to get the momentum eigenstate, we have to sum over all position eigenstates, because it's really the total plane wave, so we have to sum over all positions in space. Now you might think there's something odd between the sum and position. That's because you might go, well, position is continuous, so we shouldn't have a sum like this, because it's implying that there is only a discrete number of position states. And indeed, technically there should be an integral, but the integral doesn't add much apart from mathematical complexity. This equation gets across the core idea. Admittedly, if you're going to do calculations, you might need to replace a sigma with an integral, because position is actually continuous. But in terms of building field operators, this is a good equation to start with. So, if we want a field operator, what we essentially have to then do is replace our states, so our momentum and position states, with operators, rearrange and leave the summation alone, but bearing in mind, if we're now trying to find a field operator, we're getting a field operator by turning the position state into an operator, and because we've got the position state, we have to rearrange, and so the summation will go to the other side, and therefore be a sum over momentum states instead of position states. And similarly, because the sum has to go to the other side, also the e to the ip dot x has to go to the other side, meaning we have an e to the minus ip dot x. And in both of these equations we have the term 1 over the square root of v to deal with the fact that there has to be a probability of 1 of finding the particle somewhere in space. That is, if the particle exists and we were somehow put detectors at every location in the universe, the particle would show up in one of these detectors. So here what we've done is we've replaced states with operators, and we're free to do this providing we do this consistently. Our equation still makes perfect sense, but it's this act of replacing states with now operators which we call second quantization. Second quantization is where, instead of replacing observables with operators like you do in standard quantum mechanics, a process called first quantization, you as well now turn states into operators, and that's what's called second quantization. Really taking inspiration that quantization, at least in abstract form, is taking something that is a function in some way or a state in some way, and turning it into an operator. And this is second quantization because it's the one after the standard one in quantum mechanics. So we've talked now about second quantization a little bit, but before we go on to talking about it more fully, we'll first go back to first quantization. That is constructing operators in quantum mechanics and what standard operators in quantum mechanics do. So in quantum mechanics, we describe the state of a system as some kind of vector. Typically, when an observed system will be a vector with multiple components, each of the components referring to the probability of finding the object in a particular classical state. Although due to phenomena like kind of emission of light from atoms, neutrino oscillation, and so forth, we know that in such cases, whilst unobserved, the state of the system isn't in a classical state, but is in some mixture described by this generic state. But we can think of all possible kind of states that a system could be in, including states when it's observed, states when it's unobserved, and collectively all these states together form like, a bunch of vectors. And we call this bunch of vectors a Hilbert space. And the role of an operator in quantum mechanics can either be to measure something about that state vector, to extract some information from it, such as when the measurement occurs, but more generally operators tend to, and at least if we're thinking about dynamics in quantum mechanics, they're about changing the state of a system from one vector to another, but both vectors have to live in the same Hilbert space. They have to live in the same Hilbert space because an operator can't change the state of a system into a state which it can't possibly be in. So the new state also has to be in the Hilbert space. And also a operator can't change the state, say referring to momentum, into a state referring to position. It's like position can't turn into momentum or vice versa. So it has to be the same Hilbert space. So a operator takes a vector into another vector in the same Hilbert space, and this is really talking about the transition from an initial to final state. And in quantum field theory, we'd like to do something similar with particles, but we have to start with standard quantum mechanics. And in standard quantum mechanics, you represent the strength of this transition, so how likely a particle is to go from, let's say, a state J to a state I, using something called a matrix element, and we have our equation for the matrix element here, and in fact we write, once we have all the matrix elements, the operator as a matrix, with these components, and the operator takes the form of a matrix because matrices generically have the role of changing a vector into another, and because vectors are associated with states in quantum mechanics, operators, at least first quantized operators, are associated with changing one state into another state. So these operators cause evolution, and the matrix elements correspond to the probability, or if you like, the strength of this evolution. And if we want to write matrix A explicitly in terms of its states and the matrix element, then we need to actually introduce something called the identity matrix. Now, the special thing about the identity matrix is it will take any vector, doesn't have to be one in the context of quantum mechanics, but any vector, let's say A, providing A is, has as many columns as it does rows, so is a square matrix. In other words, then if we multiply A by the identity matrix, we will always get back A, and this works for all operators. And the brilliant thing is, we can write our identity matrix in terms of states, and thus bringing states into our description of A more explicitly. So the states tend to represent classical states here, at least alpha does. And the thing is, because a particle has to be found in one of its possible classical states, it turns out that's equivalent to saying if we sum over the product of the state alpha and its complex conjugate, then and we do this summing over all possible alpha states. That's all classical states associated with the observable alpha, where alpha could be, energy, momentum, whatever you like. We will always end up with the identity matrix. And we can think of the same particle as having another observable associated with it. That's an orbital angular momentum. And we could again write the completeness relation in terms of orbital angular momentum classical states. But because this is a different observable, the states will be labelled with a different character, that's a beta. And then using this, we can actually go, well, we can rewrite A in terms of the matrix elements and the states, because A will have to equal, thanks to how the identity matrix works, the identity matrix times A times the identity matrix, but we can express the identity matrix in terms of a sum with regards to our classical states alpha and our classical states beta. And then what we do is we notice in the middle term we have alpha A beta, which is our matrix element of A, and therefore we have an expression that A is equal to the sum over the matrix elements multiplied by the alpha state corresponding to the matrix element and the emission conjugate of the beta state referring to the matrix element. Now, we can kind of think of this quantum mechanically, i.e. in terms of first quantization, as matrix A is a collection of elements where each element has a term called the matrix element referring to how likely a transition is to occur between states beta and alpha, i.e. the particle going from state beta to state alpha. And then this kind of like alpha state, beta conjugate, emission conjugate I should say, thing is essentially telling us where this matrix element A alpha beta has to go in our matrix expression for the operator A. So we have now quantized, well, we've now shown how first quantization works. We take a classical observable, we get the matrix elements from it by considering how this classical observable acts on classical states to get a matrix element, and then we can always write the first quantized operator as a sum over the matrix elements in the relevant positions of our matrix, and the matrix elements tell us about the probability of a transition occurring where a particle goes from state beta to state alpha. And if we want to turn this into a description of an operator that's responsible for creating and destroying particles in particular states, then our matrix element will start to refer to the probability of that happening. Sorry, that's my dog barking. Or if you like, the strength of the interaction whilst, I do apologise for my dog Molly, whilst our alpha and beta states will be replaced with field operators or creation and annihilation operators. So to summarise kind of what we said about second quantization, really before, we said that in second quantization we need to replace classical states, say alpha and beta states, with operators. And we have an expression before of expressing a generic operator from first quantization in terms of sets of states alpha and beta. And we can kind of think about this as almost the creation of a particle in state alpha and the destruction of a particle in state beta. And so we can see that the form we had our matrix in on the last slide, as a sum over alpha and beta of the components of the matrix multiplied by the ket of A and the rho of beta is the kind of form we would actually like to then undergo second quantization, such that our operator starts talking explicitly about the creation and destruction of particles if we replace our alpha and beta states with operators which will create or destroy particles in these particular states. And so the operators we kind of pick, as I said, are associated with creating or destroying particles, so they'll usually either be the creation-annihilation operators or our field operators. And as quantum field theory explicitly refers to multiple states, we do indeed want the capacity to refer to multiple particles and have the operator we get from second quantization acting on multiple particle states instead of kind of an operator from first quantization acting on a single particle state. So we don't want a Hilbert space, we want something more general that can deal with multiple particles, and we call this generalization kind of the Hilbert space to account for multiple particles of Fock space. And so our second quantization operator will act in this Fock space, and as I say, to do second quantization, we look at our first quantization operator, and we replace all our states with corresponding kind of operators that can create or destroy particles. And so we then end up with this expression for the second quantized form of our operator. Now, all operators within quantum field theory will have this kind of form. Now, they might have more terms if there are more things to consider, but it's this general idea of some kind of matrix element, a creation operator and an annihilation operator. Depending on the operator we're second quantizing, there might be multiple creation operators and multiple annihilation operators, but you'll always have something in this form, and if you're creating particles at particular points in space, you'll get field operators in the place of creation or annihilation operators. So that's what our operators will look like in quantum field theory, and this is important because this now gives us a roadmap to go from quantum mechanics to quantum field theory. And as quantum mechanics is so firmly rooted, this is very advantageous. And the interpretation of our second quantization operator is it essentially removes a particle in our beta state, because you see we have an annihilation operator for a beta state particle, and it creates a particle in an alpha state. And it's worth saying if those two particles are the same type of particle, that to us will look like just the state of the particle changing. So now we talked about second quantization, and we also mentioned a Fock space. Well, we said that generically we want a second quantized operator to work within Fock space, but if we look at the second quantized operator we have on our screen, this operator is referring to the creation the annihilation of one particle and the creation of one particle, possibly the same particle. So this doesn't really encapsulate generically what an operator will look like in Fock space. So let's look at second quantizing an operator that explicitly refers to multiple particles to see more generally operators in quantum field theory. So we mentioned that kind of in terms of classical physics at the start of this video, there's something there's some way of describing the potential in quantum field theory. Now, the the potential might sound an abstract thing, but really the potential stems back to very directly observable phenomena. So it's like if you've got a spring and a mass attached to it, and you compress the spring, and you somehow wrap, tape around the spring or something to hold it in place. There's tension in that spring, and there's energy associated with it. And the moment you cut that sellotape, the spring will, fire off, and the mass will be flung into the air. And so there's like energy stored in the spring, right, waiting to be released, and we call that potential. And if you know the force, you can work out the potential energy, but also if you know the potential energy, you can work out the force. So classically there are two equivalent ways to talk about, but mechanics you can talk about in terms of forces or in energy, like, even with gravity you can pick Newton's law of gravity that makes reference to forces, or you can use Poisson's equation, which is kind of equivalent, but Poisson's equation makes reference to the gravitational potential. So the idea of potential, or more fully potential energy, is fairly familiar. It's just kind of in quantum mechanics, we can't really talk about the idea of forces very well anymore because it relies on the idea of acceleration and therefore on the idea of a particle's position changing, but because the idea of where a particle is fuzzy in quantum mechanics, the notion of acceleration is a very good one, so we have to abandon the idea of forces, and so we're really stuck with the idea of potential. So in quantum mechanics, all the equations make reference to potential, they do not make reference to forces. So when we're talking about forces between objects in quantum mechanics, we're really describing it in terms of a potential, and we represent the potential as an operator. And for those of you who have done lots of quantum mechanics, you'll know that actually the operator for the potential, because it's a function of position and the operator for position is the same as the position coordinate, it turns out that the operator for potential is just the classical potential function. So you can take the equation for the potential associated with the force and just use it directly in quantum mechanics with no amendments. This will not work in the case of quantum field theory, however. But quantum field theory is still trying to describe the idea of potential, but when we second quantize it, remember we're talking about the creation or destruction of particles in particular states, and therefore really the potential stops being a description of some kind of force, and it stops being even continuous. In fact, the potential becomes a description of particle interactions. So you have to drop the idea of field lines, like we can see in the coloured diagram above, and start thinking of two test particles as exchanging force-carrying particles, and that being our model for how forces seem to arise in the universe. But now we talked about conceptually what the second quantized form of the potential is, let's go into the maths of actually working out an expression for it. So the potential traditionally, to make matters simple, is treated as acting solely between two particles. Each particle is going to have an initial state and also a final state. So in total there are 4 states to consider, 2 initial and 2 final. And so we want a second quantized operator in flux space which is going to act on 2 particles, and this will be the generic form of such an operator. Now you see here it'd be very hard to represent it as a matrix, because our matrix element has 4 indices, so the idea of representing operators as matrices has kind of gone out of the window by this point. But we can see that we've got, our creation operators, matrix element, and our annihilation operators. Now, our creation operators are always to the left, thanks to something called normal ordering. And normal ordering prevents essentially the minimum value for the observable with this operator associated with it being infinite. So for our purposes, it avoids there being infinite potential energy, which, you know, in the context of quantum field theory, because it's only concerned with energy differences, isn't too important. But in terms of relativity, you know, energy is related to the curvature of space-time, so we really don't want predicting infinite energy as our baseline. Hence, we use normal ordering. I won't prove it here, it's easier to prove if you have a second quantized operator acting on a single particle, such as the one we saw, you know, just now in the last part of the video. But you can prove it for this kind of operator too. And an example of this kind of operator is, as we said, the potential. But the potential is a function of position classically, and so we really should think of it as creating or destroying particles in particular states at particular locations in space. And therefore we replace our generic creation and annihilation operators with field operators. The other thing we'll do, we'll replace our sum with an integral, because space is continuous even within quantum mechanics, and even quantum field theory deals with, you know, particles moving in a continuous space-time, so space is still continuous. We're not trying to do quantum gravity, we're not quantizing space-time itself. We might be quantizing the fields in space-time, but not space-time itself. And therefore the summation needs to be replaced with an integral. And we need to integrate over space, so we have terms like d3x, meaning integrating over, you know, the volume of space for one particle, where its position is measured in terms of, you know, a coordinate system, and we'll also have, you know, d3y for integrating over the, you know, volume of space with regards to the other particle. And also, to prevent double counting, now we've got two particles, we'll also need a factor of a half. Such that, say we've got particle B, we don't go, well, A kind of exchanges a particle with B, so there was one particle of B, but also B exchanges a particle with A, so now there's two particles of B, even though we just said there's a particle A and particle B, so there should only be one particle of B. So, to prevent double counting, we need a factor of a half, really. And this leaves us with this expression for the potential. And as we've said, the physical meaning of this potential is really we have to abandon the idea of field lines and start to think about forces as the result of exchange of particles. But we also know that scattering is kind of, just particles bouncing off each other and entering different states. Which we might describe by forces, but we've also said, well, we use these operators when we're talking about processes where new particles are genuinely created or destroyed. And what this means is, in quantum field theory, thanks to the fact that we are describing forces, that is, interactions between particles, as the creation or destruction of force-carrying particles, it now means that there is a fair bit of unison between scattering processes and things like particle decay, things that one might not, or like annihilation and pair production, things that one might not think of as being connected, because in one, we aren't creating or destroying particles seemingly from a classical perspective, and in the other one we are. But we know in quantum field theory we're creating and destroying particles in both cases. It's just in one the particles we're creating are force-carrying particles, in the other they're matter particles. And what that means is, for example, if things like electron scattering is allowed, well, that has to be caused by the exchange of photons, and therefore, not only should electron scattering be allowed, but things like electron absorption of a photon, or even an electron and positron meeting and forming a high energy photon. So suddenly we see why, when you have scattering processes, you also have particle creation and destruction processes. It's because, in reality, everything is described by creation and destruction through our annihilation and creation, or equivalently are field operators. And that's the beauty of quantum field theory. So in the next video we're going to park the discussion of quantum field theory per se and go back to some classical origins, but we will link it back to quantum mechanics, and we'll be exploring the Hamiltonian and looking at Hamilton's equation, and I'll try to mention a little bit about chaos, even though it's not mentioned in the book, because that's a very good application of Hamilton's equations. But this has been everything for second quantization in this video. There's been a lot of mind-bending stuff, so have a good break. I know it's a long video, but we get into some really meaty details here, so hopefully see you for more soon.